Hi, today I will talk about dynamic mechanical analysis with Nanoindenter. At first, I'll give a brief introduction about what dynamic mechanical analysis, or in short DMA, is. I'll talk briefly about nanoindentation and why both of these techniques can be combined together to characterize material properties. So first of all, moving on to DMA. What is DMA? It is a technique that measures the mechanical properties of viscoelastic materials as a function of temperature or frequency under the action of periodic force or displacement. We'll get to understand this statement a little better in the course of the presentation. So I mentioned that DMA measures the mechanical properties of viscoelastic materials. So why do we use viscoelastic materials for DMA? These kinds of materials are a little complex to characterize because they have both elastic behavior and viscous behavior, and the response that they show is a complex interplay of both elastic and viscous response, and hence we need DMA to characterize them. An example of such a system that is viscoelastic in nature is polymer or polymer-based systems. So DMA works by applying a sinusoidal or oscillating stress to a sample and measuring the resulting strain. From the diagram here, we can see that there is a phase difference between the input stress and the output strain, and the amplitude of the output strain is different from the input stress. The amplitude basically depends upon the storage modulus of the system. When it is higher, the reduction in amplitude of the output strain is going to be lower as well. We can see that the response is sinusoidal or periodic in nature, and they can be characterized by the sine function. So in a viscoelastic system, we have a viscous response, viscoelastic response, and an elastic response. And so we need one term that can pack both of these responses together in a single equation, and this is what we get from the complex modulus. So breaking down the complex modulus into its individual components, we have two parameters. One is the storage modulus, which refers to the elasticity of a material, and it tells the energy stored during one period under a load. And then we have the loss modulus, which refers to the plasticity of a material, and it is proportional to the work lost during one period under the load. Additionally, we have the loss factor, which characterizes internal friction or mechanical damping. So it's the storage modulus, and loss factor that are used to characterize the mechanical properties of a system in DMA tests. So this graph over here shows how a typical result of a DMA test looks like. We have the storage modulus and the loss modulus plotted against varying temperatures. So temperature is not the only parameter that can be varied in DMA. It is also possible to measure how the properties vary with changing amplitude and changing frequency as well. So DMA helps us to analyze the characteristics or the change in characteristics of a material under changing conditions, which is useful for understanding and simulating their behavior in real-world applications where parameters like temperature do not really stay constant, they are continuously varying. So moving on to this graph over here, we can see that there are three distinct regions for the material behavior with changing temperature. The first is the glassy region, where the storage modulus is relatively high and constant. This tells us that the material is rigid. Then, as the temperature continues to increase, we see the glass transition region, where there is a sharp decrease in the storage modulus, and we can see the transition from glassy to rubbery behavior. Lastly, we have the rubber elastic plateau, where the storage modulus levels off at a lower value, and this tells us that the material has become soft and flexible at really high temperatures. Now moving on to nanoindentation. What is it? It is a technique that is used to measure the mechanical properties of materials which are really small in volume, like thin films, coatings, or single crystals. A sharp indenter is basically pushed into the material surface with a controlled force, and a machine is used to record the force applied at different depths of penetrations. And when the indenter is withdrawn after being indented on the surface, it is also recorded how the material recovers. So we get a loading-unloading curve from the nanoindentation experiment, as we can see from the graph over here, and this helps us to characterize and find out the local mechanical properties like hardness and elastic modulus. So DMA is basically used to characterize the bulk mechanical properties, whereas nanoindentation helps us to calculate the mechanical properties in really localized regions. So when we combine both of these techniques, we can find out how the local properties of a material are changing in dynamic conditions where the temperature and other parameters are changing. So how do we conduct nanoDMA? We can do this with different devices, but I will be showing how we can do this with an atomic force microscope or AFM. So in an AFM, we have a cantilever with a tip attached to its end as shown in the figure over here. And the cantilever is made to oscillate at a certain frequency and a certain amplitude on the surface of a sample. And there is an interaction going on between the atoms of the tip in the cantilever and the atoms of the surface. Depending upon these interactions, there is a change in amplitude and hence a change in the response of the cantilever. So basically, the input response given to the cantilever and the output response, which depends upon the material's interaction with the tip of the cantilever, we get different kinds of response for the input and the output. And this is what is basically being measured and compared to find out the properties like the storage modulus, loss modulus, and the loss factor. And this graph over here shows us a typical map of the storage modulus and loss tangent that is measured with nanoDMA in AFM for varying temperatures. So this was taken in localized regions of a sample that consisted of polypropylene matrix with a cyclic olefin copolymer. And if we look closely over here for the diagrams at 25 degrees Celsius, we don't see any contrast. And the colors are almost similar. This tells us that the storage modulus and the loss tangent are both the same for both of the materials at a temperature of 25 degrees Celsius. However, as the temperature increases, we can see that certain regions are lighter and certain regions are darker. This is because when the temperature changes, the local properties change depending upon the material that is present. And this becomes really important because it helps us to understand how in changing different conditions, the local properties change depending upon what materials are present. And the materials that we use today are complex systems because they consist of many different materials together. So the properties of complex systems are no longer homogeneous, and the local properties can be different depending upon the material that is present in the system. And this is why nanoDMA can be a really powerful tool to characterize the materials that we use today. So this shows a summary of how the parameters are calculated in nanoDMA. And the main advantage is that we get nanoscale resolution, which is beyond the reach of conventional DMA method. We also can analyze small sample volumes, like we can characterize thin films, coatings, microdevices, and even individual cells or nanocomposites. NanoDMA provides continuous measurements of mechanical properties as a function of indentation depth, frequency, and time, revealing how materials respond dynamically at different scales and conditions. And hence, this makes it an important tool for characterizing materials that are used in advanced applications. So by matching nanoscale viscoelastic measurements to bulk DMA data, nanoDMA helps to bridge the gap between local material structure and microscopic properties, supporting better material design and failure analysis. So this was it for my presentation. Thank you very much for your patience, and I hope that you learned something from it.